moment ago that things look a little bit different. The very first thing that you should notice, especially when trying to graph, is there's no y equals. Instead, there's an r equals. What does r stand for in polar mode? R stands for radius. And then, of course, we have a function of theta, and theta is our, you could think of it as our independent variable, kind of like x. R is our dependent variable, kind of like y. But you're going to see the similarity is not as close as you might think. Theta is my angle of rotation. Angle of rotation from standard position being the positive x-axis. We'll see in a second. So we have a radius as a function of theta, okay? Going in between, first of all, just relating it to what we do know, going between rectangular and polar. For a rectangular point, we know this. For a rectangular point, you go a horizontal distance, you go a vertical distance, and you get to the point xy, right? Polar, a little bit different. You turn from a standard position, you turn a certain angle, and you go out a certain radius, which depends on the units. But radius, you'll see it in a second, you go out a certain radius. Whatever that radius is, whatever that distance is, that would be the point r theta. Turn a certain angle, go out a certain radius. You'll see it in a second if you haven't before. Turn a certain angle, go out a certain radius. Now hold on, that's weird because r is like y, so why does r come first? Just the way that polar works, I don't know.
So then the theta is turn a certain angle, right?
Theta is turn a certain angle and r is go out a certain radius. Now we're going to see a couple weird things about going out because that's like, okay, whatever, just go out. But you have to kind of switch your thinking of positive and negative with radius as well, but we'll see that in a second. Conversions between polar and rectangular. They should be pretty easy because all they are trigonometric, right? Because to find x, I can do cosine adjacent over hypotenuse. So x is equal to r cosine theta, y is equal to r sine theta, just using trigonometric ratios. I know that r squared is x squared plus y squared with Pythagorean. I know that tangent is equal to y over x, being careful of quadrants, etc., etc. But these are my conversions between polar, and going different directions, but polar and rectangular. And technically, kiddos, not that it should be a huge deal, but just because I am worried about how many of you have not had as much coverage of this in pre-calculus, I am going to make this an endeavor. But hey, it's an easy one, hopefully. The picture might help. If you want the picture, it's up to you. But this is going to be endeavor number, Chelsea's been gone, so we're a little behind. What is it, 30?
32.
32?
Yeah.
Oh, because we had some stuff with vectors, that's right.
Wait, actually it might be 33.
I thought 31, 32, I think, right? Was there another one?
This one?
Yeah, that was the last one, I think, with vectors, right?
Yeah.
What was this one?
Conversions between polar and rectangular. You can use the picture, it's up to you. Alright, we're going to graph a few polar points and just kind of talk about the ins and outs of polar because there's a few different ways. Rectangular is like whatever. Positive x means right. Negative x means left. Positive y means up. Negative y means down. Polar, a little different. Sorry. Did you do it? No, you have a question. There are a couple other things that are going to come back. And a couple other things are going to be these two trig identities. These could come back to haunt us just a little bit. But guys, don't we already have these ones written down? What are these? Power reducing.
Oh, yeah.
Power reducing. We already have these somewhere. Just a quick reminder. Power reducing, we wrote them down for trig integrals, right? Trig integrals. So power reducing, we already have that, just reminding you of them. Okay, polar. Question. I would give you polar graphs. Do you guys have any polar graphs in your notes? I don't remember. Like just blank ones? Lame sauce? No, that's okay. Alright, approximate. You don't have to draw all the circles necessarily, but approximate, or at least tell me, kiddos, if I wanted to graph the point, let's say 545. 545. Where would I put the point?
First go to 45, right, and then out.
And actually, just to be more particular, let me do 5 pi over 4, okay? Because we are doing radians, even though it's easier to think sometimes in degrees. Where would this go?
So point that way.
Okay, this way.
The 45,
Go to the 45. Then what?
and then out 5 from the middle.
Out 5. So out 1, 2, 3, 4, 5. Right? Is that okay? Alright, what if I was to give you instead the point, let's do another one. 7, 2 pi over 3. 2 pi over 3, second quadrant. What reference angle?
The second one.
Second quadrant, and where would it go?
120.
Okay, 120, because 2 pi over 3 is 260, so I'm going to go out how much?
7.
4, 5, 6, 7, right? I think. 1, 2, 3, 4, 5, 6, 7. Good. What if I was to give you the point? Let's do that. Hold on. Where would that one go?
That way.
Is in the middle.
You could say 11 pi over 6 would be 30 degrees under, right?
Yes.
But the problem is, where's 0? Right there, right? But hold on. Can anybody give me another point that would be in the exact same place? What's another point that would be there? 0 pi over 2. What else?
0 pi over 3.
Okay, hold on. How many places are going to have the exact same place? Infinitely many, right? Because I could have any angle, and I could go around twice or go around 3 times, right? Any angle with radius of 0, oh stink. So I could have R be 0 and the other one be infinitely many answers? What if I was to give you something like, the point -7 and 5 pi over 3?
First go to 5 pi over 3.
First go to 5 pi over 3. Where would that be?
300.
Third quadrant?
Third quadrant. 5 pi over 3 is 1 pi over 3, 160 degrees away from 360, which would be at 300. Now what? Go out. 1, 2, 3, 4, 5, 6, 7. Here?
Or the opposite.
If I go out, I'm going positive. So if I go towards 300, I'm going positive. What's this tell me? Not positive, but negative. So instead of going positive to 300, I'm going to go negative 1, 2, 3, 4, 5, 6, 7. Stink. Can I get to any point on a polar graph multiple different ways? Yes. And that is where we're going to have a dilemma. I'm going to go ahead and split him up really quickly just so that we can see it. Group, ungroup. We'll put point here. And then we'll say 2 options, same point, right? We could keep on going, but here's the idea. First of all, when you graph, do you graph the R first? I don't know. I guess you could graph the R and then go around the circle. I always like to graph the angle first, like graph 45, graph pi over 4, go out, or graph 2 pi over 3, go out. If it's graph 300 and go backwards, right? Now you're not going to have any of these necessarily on the AP, like with lots of circles and you graph points. That's not AP calculus. But what you are going to have to do is be able to know how to graph polar curves. Let's keep going. Guys, let's go ahead and look at this. Slope of polar curves. Have we already written this down?
I don't think
How to
so.
find derivatives
Oh,
of
yeah.
polars?
I remember this.
We did derivatives of polars at the exact same time of derivatives, as derivatives of parametric. Why? dy d theta, dx d theta, does that ring any bells? dy dt, dx dt?
Yeah.
Same thing. How do I find the second derivative? Well, let's write that down for a second. How would I find the second derivative? The exact same way I do parametric. So the nice thing is polar and parametric go together because solving procedures are the same. Polar and parametric go together because solving procedures are the same. So first derivative, dy d theta over dx d theta. Second derivative, d d theta of dy dx over dx d theta again. Important to know, but we already have as an endeavor card. Now let me give you a couple seconds because the window, I'm just going to write down a couple things about the window. The window is a little different in polar in that you have theta min, you have theta max, and you have theta step. Kind of like parametric, you have T min, T max, T step, but we don't really have to graph parametric much. Polar, though, is going to be helpful in being able to graph. So I want you guys with your graphing calculators to graph each of those three and try to get the picture. Try to get the entire picture and see if you have to change anything. Maybe zoom standard good. Maybe zoom standard isn't good, so how could you change it? We're back in our notes packet, I think, guys. But I would still write down slope of polar curves in this section because it is very important. First and second derivative, we already kind of have it, but tissues all gone. Okay. More tissues.
So should we write the window stuff in our notes?
It's up to you. You can just write it in the worksheet. It's more just an understanding than like an actual memorizing thing. You guys trying to graph? I'll give you a couple seconds. Try to graph on your own. Can you get a good picture? It's funny. It's different. Not normal. If you can't see, you can change window.
Mine's not going. That's why I just changed to polar, but
Still not going. Are you in degree or rate? Well, it shouldn't be degrees.
polar, degree,
Then you put into y equals, right?
yeah, so put it here.
How do you?
Put into degree.
Yeah. Do you know degrees or radians?
Yeah, is in degree.
Mhm.
Ratings. Oh, yeah, right.
If you look at window, you saw 6.28, right?
Yeah, but where should it?
Oh, right here. 6.28 because theta is 0 to 2 pi. So that's why good for radians, bad for meters.
Okay.
You could do. You could change zoom and zoom out, or you could change
So X.
yeah,
Yeah.
to see it better, right?
Yeah.
Or probably zoom out would be good too, Kaiki. I don't know.
Okay, thank you.
Did you want it in radian or degree mode?
It's up to you. You can try both because there are pros and cons to both. Degrees, we can see intersections easier. Radians are the actual numbers we're looking for. Okay. Couple things that can change. This is well and good right now because right now I am in degrees and my window is in degrees. But if I change to radians real quick and I don't change my, kind of cool, but is that a good graph? What was wrong? I had the window tailored for degree, and then I said radian, and my graph freaked out. Why? Because I still have theta, 0 to 360. I don't want 0 to 360. I would want instead something like 0 to 2 pi. Maybe to be totally safe, maybe negative 2 pi to 2 pi. I'd rather have more than not enough. But let me just go ahead and clear it, and I'll say 0 to 2 pi. What if I didn't go far enough? What if I just said pi? Now hold on. We can still try graph. Uh-oh. Why is it still bad? Because guys, how many numbers is in between 0 and pi? 3.1415. How big of steps am I taking? If I take a step of 7.5 and I'm only going 3.5, is that going to really work? Steps are how often to graph. And so if I say graph every 7.5, well, that's not going to be good. What if I say graph every 1? Okay, 1, 2, 3 steps. 1, 2, 3 steps. But did 3 steps give me a good graph? No. So I don't want to graph only 3 steps. I want lots and lots of steps. How can I get more steps? How about 0.1? So 31 steps. Do I have a better graph?
Yeah.
Yes. So different things to keep in mind. Theta min, theta max. Uh-oh. Did it finish my curve? No. Why not? Because it graphed from 0 to pi, and I didn't go a full cycle. Now, different graphs can have different cycles. Just because you put 2 pi doesn't mean you always get the right one. But this one, 2 pi, will go through all of it. Now, here's the problem, guys, is we saw 0 to pi, and it had graphs here, and here, and here, and here. 0 to 2 pi, I'm going around to 2 pi, and I'm going backwards and forwards and all kinds of stuff. So we're going to have some issues with that as well. At this point, you could also, guys, if you do Zoom Standard says reset. And what Zoom Standard says is 10 by 10, and then it says, I look and say, degrees or radians? Hold on, let me go to window. Zoom Standard says, I know you're in radians, I'm going to make radians. Okay? And if I was in degrees, Zoom Standard, if I go Zoom and I go Zoom Standard says, I know you're in degrees, I'll do degrees. So that could be a quick reset if it's like all messed up. But we have just a few examples of polar curves. We have roses. That's what this one is. It's a rose. We have limaçons. I know it's not a rose, but it's a flower with petals, and they call it a rose.
I call it a daisy.
You could call it a daisy. How many petals? 1, 2, 3, 4, 5, 6, 7, 8, 9. How many petals, guys? 12. What happens if you change it? What happens if instead of 6, you make it 5? You would think how many petals? You would think 10. But when you graph,
Wouldn't you get less?
you would get less. I'm going to zoom in. Oh, it's going.
It's thinking.
Yeah. It's too small.
Oh, it's too small.
There we go. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Technically, between 0 and 2 pi, there are 10 petals, but what's true about those 10 petals? They're right on top of each other, so it's 5 and 5. There are really only 5 petals that result. And it might have to do with sine is odd and an odd number of petals. What if we change it to cosine? Cosine's even, right? Let's try him. Still only 5 petals. So it doesn't have to do necessarily with sine or cosine, even or odd. It has to do with the number itself. If I have an odd angle, it's only going to have that many petals. If I have an even, it'll have twice as many. That's a quick little trick about roses. We'll come back. This one's called a limaçon. French for snail. There's like a little accenty thing, don't worry about it. But it's a limaçon, French for snail. Limaçons can have these little inner loops that occur, and they're going to be pretty important. Then you could just have like an ellipse. You could have an ellipse, you could have a circle, you could have a few different things. But those are just a few. You guys already saw cardioids as well, the little like heart shape. Now kiddos, hold on. What's going on in example number 2? Example number 1 is just, can you do your graphing calculator? What's example 2 say? Find the slope. Oh, slope. Easy. Derivative. Got it, right? Okay, so how do I find derivative? Because when I'm talking about slope, I need dy dx, right? What's the problem? I have r's and betas. Well, how do I get x's and y's? You change it to conversion. That's why we made it an endeavor. How do I make y? Y of theta equals r sine of theta. How do I get x? Wait a minute. But if I take derivative right now, d theta, there's an r. Oh, what do I have? An r. So then I plug in and I say x of theta is equal to 2 sine of 3 theta cosine of theta, and r sine of theta, 2 sine 3 theta sine of theta. Does that make sense, kiddos? So if I need to take a derivative, and this is super important, so don't lose track. If I need to find a derivative of a polar curve, if I need to find the slope of a polar curve, I need to take or find x and y first before I can ever start doing the derivative. So it's kind of weird because I have to discover what to take derivatives of. But I discover them. I use my formulas, and now I have x, I have y, so now it's time to take derivatives of x and y. I'm going to do a couple shortcuts real quick. Derivative of y is going to end up being 6 cosine 3 theta. I need product rule, right? Sine theta plus 2 sine 3 theta cosine theta all over 6 cosine 3 theta cosine theta minus 2 sine 3 theta sine theta. That's just product rule, right? But where are they asking me to find the slope at? Okay, so my such that. Hey, is unit circle still important? I know. I'm sorry. But yeah, unit circle is still important. Plug and chug. You guys got it? So we're in notes. We're on example 2. Yeah, example 2. So then my plug and chug, I end up with 6 cosine of pi over 2 sine of pi over 6 plus 2 sine of pi over 2 cosine of pi over 6. Nope. Minus. Oh. There we go. Nice thing is, pi over 2 is 90 degrees, right? So at 90 degrees, what's cosine of 90 degrees? 0. So I can say, haha, 0, right? And haha, 0. In this example, sine of pi over 2 is 1. Sine of pi over 2 is 1. Cosine of pi over 6, cosine of 30, what do you guys got? And sine of pi over 6? Yeah, 1/2. So I can say, okay, equals, and this is just dy dx, this is just slope. Whew, got it though. Root 3, because 2's cancel, all over negative 1. But what do they want me to do with that? Use it to find the equation of the tangent line, right? Wait, how do I, at pi over 6? I know negative root 3 x minus, how do I get x1?
Where's the point?
Where's the point? I don't have it, but what do I have? Pi over 6. What can I do with pi over 6? Plug it in to where? X of theta and y of theta. Because once I found x of theta and y of theta and theta equals pi over 6, I have all my pieces to the puzzle. So I can say, oh, plug in pi over 6. Oh, plug in pi over 6. So I'm going to have x1 time to plug and chug. And when you plug and chug, you can go ahead and say, or my x and y equations, just for sake of time, x equals ruh-roh. Dang. So I have to plug in, and I could say x of pi over 6 is equal to 2 times sine of pi over 2, 2 times 1, times cosine of pi over 6. And we did this a second ago, I think. Y of pi over 6, plug in 2 sine of pi over 2 is 1, times sine of 1/2 times 2 is 1. And that's just kind of off to the side, right? I can go ahead and plug in. So then y minus root 3 equals negative root 3 x minus 1. Did I switch them? I did switch them. Done. You guys kind of seeing how things change a little bit with polar? Still have x's and y's, but not at first, not naturally. You usually have r equals, and so we go from r equals to x and y using conversions. Then we can do dy d theta over dx d theta and solve, etc., etc., etc. Can I keep going?
Yes.
Okay, example number next one. Convert. Hey guys, get your worksheet out. I might do a couple for you. Worksheet 10b1. Maybe not all, but a few. Let me see your notes real quick, man. I see notes. Why am I pausing, guys? What's next on notes? Do you see what's next on notes? Area. Integrals? Nope, not yet. We're not good enough yet. Okay, here we go. 10b1. Let's do a few examples. Number 3. Convert. How? Plug what in? I need r of theta. R is equal to 5? Okay, that's one way. You could say, wait a minute, x squared plus y squared equals r squared. R squared. So I could just say r equals 5, so r of theta equals 5. Done. Wait, that was way too easy. Hold on, is there another way? Kiddos, look at your conversions. What does x squared plus y squared equal? X squared plus y squared is? Got it. This might be a little bit easier, huh? So r equals plus or minus 5. Technically, if we were solving. But guys, what shape would r equals plus or minus 5 in polar give us? A circle, right? So then when I say plus or minus 5, I could just say positive 5. Technically, probably this one is the most correct. But Ethan, when you saw r equals positive 5, you were right, but r, radius of a circle, always positive. But r in polar could be positive or negative. Does that make sense? That's why technically, even though r is 5, I would say r of theta, even though r equals 5, in circles, normal circles, radiuses don't have to stay positive anymore because you can go positively towards an angle or negatively the opposite direction. How about this one? What would you guys do if it says convert to rectangular form? Uh-oh.
Make it either cosine or sine.
R cosine, so it's x equal to 3.
If you're totally stuck, I would look at the triangle and say, I know how x and y and r and theta all go together, right? Right triangle? How do I get secant of right triangle? What's 1 over cosine of this triangle?
R over y over x.
R over x. Wait, does this make sense? You can use the triangle to say, what is secant? Secant is 1 over cosine. What's 1 over cosine? Well, 1 over cosine is reciprocal of adjacent over hypotenuse. Choshikao. Sha. Hypotenuse over adjacent. There we go. My pre-calers, you know choshikao. It's like sokotoa, but for the reciprocals.
I still use that.
Yes. So then r equals 3 times r over x. Uh-oh. This isn't rectangular yet. No, but it's closer. What could I do? Times by x, divide by r, x equals 3, right? Guys, 10b1 takes you on a journey of basically converting, finding derivatives, finding vertical, horizontal tangent lines, and seeing if you can figure out how to sketch. We're going to start tomorrow with what are the different common sketches because we are going to have to sketch polar and then area tomorrow, okay? So tonight, work on 10b1. 10b1 is like pre-cal review. For my ones that are like polar, or polar hasn't been, well, it's been a long time. Use 10b1 to review. Sound good?
Okay.
All right, cool kids. Come in tomorrow ready. Because we're going to go over your pre-cal. We're going to go over 10b1. See if you have any questions. And